Today we're going to learn how to read a pedigree and how to solve pedigree problems. Marfan syndrome is an inherited condition that affects the connective tissue, resulting in unusually long bones and spinal curvature, as well as vision, cardiac, and respiratory problems. In fact, Abraham Lincoln had Marfan syndrome. That's why he was so tall and slender. The syndrome tends to become increasingly severe over time. The following pedigree shows inheritance of Marfan syndrome in a multi-generational family. So if it's colored in, these people have Marfan syndrome. If it's not colored in, they do not have it. So how is this syndrome inherited? In other words, is it dominant or recessive? Well, it's in every generation. And there are no cases where it skips a generation and then comes back later. Therefore, this must be a dominant trait. Can you determine individual 2-4's genotype? Roman numeral 2, person number 4. So this is the second generation and the fourth person listed. Here's what I do when I'm trying to solve a pedigree problem. First, I write down what I know. I know that if it's colored in, that you have Marfans, and we have decided that is dominant. If it's not colored in, the person does not have Marfans, and that is recessive. Since Marfans is dominant, we're going to use a capital M to represent the dominant trait and a lowercase m to represent the recessive trait. I find it easiest to start with all the people who are recessive. In order to be recessive, they must have 2 copies of the recessive gene. So I'm going to put lowercase m's above everybody who is recessive. Now, each person who has the dominant trait must have at least 1 copy of the dominant trait and maybe 2. So for now, I'm going to put 1 copy of this dominant capital M for each of the shaded in people. Now let's see if we can figure out the second letter by looking at what happens with their children. Notice that each kid must have gotten their dominant capital M from their dad. Therefore, the mom had to pass on a lowercase m to each of her children. So we're going to include a lowercase m for all 3 of them. Do we know the dad's second gene? No. Now, he has a high probability of having 2 capital letters since he passed a capital dominant trait to every single one of his kids. But we don't know for sure. Just like families can have 3 boys or 3 girls, well, they could also have 3 kids with Marfans, whether the dad has 1 gene or 2 genes for Marfans. Therefore, we don't know his second gene, even though it's likely to be a capital M. Now let's figure out the grandchildren. Each of these kids has a lowercase m. They definitely received a lowercase m from the dad. They must have received the other from the mom, so we know we did this right because the mom passed on the lowercase rather than the uppercase, yet she still has this trait. Let's look over here. This dad definitely passes on a lowercase m to every kid. So there's a lowercase m, so this child and this child must also have a lowercase m. The mom passed on a capital M to these 2 kids and a lowercase m to this kid. So we know we did it right. Now, Can you determine individual 2,4's genotype? Second generation, fourth person. Oh, capital M, lowercase m. You don't need to bother explaining because writing in the genotype for everybody basically does explain it. Individual 2,1 and 2,2 are considering having another child. What is the probability that this child will have Marfan syndrome? Explain using a Punnett square. So first we need to look up individual 2,1 and 2,2. So second generation, first person, that's lowercase, lowercase. This is the male. You usually put the male on the top of the Punnett square, but if you put him on the side, it's okay. Then the female has a capital M lowercase m. She usually goes down the side. Now do your cross. And you can see 2 of the children have Marfans and 2 do not. So this couple has a 50% chance of having a child with Marfan syndrome. Remember, you must show the Punnett square and give the percentage to get the answer right. Number 2, examine the following pedigree showing the inheritance of straight hair in a 4-generation family. So if the person is colored in, they have straight hair. And if they are not colored in, well, the opposite of straight hair would be curly hair. Okay. Look at these generations. Did they ever skip a generation? Sure they did. They skipped it here, here. What's going on here? Why is there a triangle? Well, these are identical twins. These girls should either both be colored in or both not be because they are genetically identical and they share the same DNA. So is straight hair a dominant or recessive trait? Did it skip any generations? Yes, it did. So it must be recessive. Now identify the genotype of each individual in the pedigree. Whose genotype can you not be certain of? So let's go back up here. Straight hair is colored in, and straight hair is recessive. So we're going to put recessive, and curly hair is dominant. So we must put a capital C for curly for dominant and a lowercase c for straight hair, which is recessive. Remember to exaggerate the size of your letter C so you can tell the difference. Now start with all your recessive individuals because they definitely have 2 recessive genes. So each person with straight hair has 2 recessive genes. Now, each person with the dominant trait must have at least 1 capital letter. So we're going to put 1 capital C for each person who does not have straight hair. Now we have to figure out the second gene for each person with the dominant trait. By the way, what's this double line? Well, notice these are the grandparents. They had 2 daughters. The daughters got married. They had kids. And the cousins married each other. Oh my goodness. So whenever there's a double line, this shows inbreeding. If there is a rare recessive genetic trait, and it's a very rare one, usually people won't marry somebody else that has that same rare trait. But if they marry a relative is more likely to have that recessive rare trait. And then one of their kids could come up with that trait. Now, if it's just straight hair or curly, no big deal. What if that recessive trait was like the gene for low oxygen and your kids ended up being blue like the Fugate family? They happened to have a very rare recessive trait. They got married, they weren't related, the first couple was not related. Then they had kids, and then their kids married some cousins as they went down the line because they were so isolated out in the country. And so that's when that trait came back. If they had married outside the family where that gene was very rare, the recessive gene never would have shown up. This is why purebred dogs often have problems. For example, Labrador retrievers often have hip dysplasia. This is a rare genetic trait, but to get a purebred golden retriever, you have to breed it with another golden retriever, and all Goldens are related to each other. So therefore, those rare recessive traits become more common because they keep popping back up in the descendants of those golden retrievers. These parents had a kid with 2 lowercase c's. So this parent must have donated one of the lowercase c's, and this parent must have donated the other lowercase c. Therefore, the grandparents are heterozygous. These children received a capital C from their dad. They had to receive a lowercase c from the mom. Now, with 4 kids and all 4 of them getting a capital C, we have a very high chance that their dad has 2 capital C's. But do we know for sure? No. So probably capital C, but not for sure. So we're going to put a question mark. So this C is definite. The next thing is a question. We don't know the second letter. This is one of the individuals of whose genotypes we are not certain. Let's look at their other daughter. She married a man with a capital C. If these 2 kids have a capital C, they both got it from their dad, so they must get a lowercase c from the mom. Once again, we don't know the second letter, and really with only 2 kids, it's hard to predict. Now let's look here. This parent had to be the one that passed on the capital C. This parent must pass on a lowercase c. Over here, this parent passed on the lowercase, so this parent must also have passed on a lowercase c. Otherwise, you couldn't have somebody with 2 lowercases unless both parents had a lowercase to pass on. This child got a capital C from this parent. They must have gotten the lowercase c from the other parent. And here, we don't know which parent they got the capital C from. And either way, the other parent has a capital or a lower that they could have passed on. So we do not know the second part of this person's genotype. We don't know the second part of this person's or this person's. So whose genotype can you not be certain of? Individual 2, 1. Individual 2, 5. Individual 3, 1. Individual 4, 1. And individual 4, 6. Letter C. If individual V3, okay, V3, V5, 3. So if this individual marries a man who is heterozygous, so she marries a man who is heterozygous, one capital, one lower. What is the probability that they will have a girl with straight hair? First of all, we need to do a Punnett square. And the dad is capital lower, and the mom is capital lower. Now, do your cross. So these three have curly hair. This one has straight hair. This is a 25% chance. Plus, they asked a girl, not a boy. There's a 50-50 chance of a girl or a boy. So technically, half of 25% should really be our answer. However, we're just going to go with what's the probability they will have straight hair. And that would be 25% chance. Number 3, humans may have a peaked or smooth hairline. If a man and a woman both have a smooth hairline, none of their children will have peaked hairlines. How is a peaked hairline most likely inherited? Okay, well, if it was a dominant gene, then they could be heterozygous. So I'm just using the letter A. So capital A, lower a. And in that case, there could be two lowercase a's, so it looks like this can't be dominant because they could have a peaked or a smooth hairline. So if it's recessive, then every single one will be recessive. So if the smooth hairline must be the recessive, then a peaked hairline must be dominant. Then the peaked hairline, a capital P, and then the smooth hairline will be a lowercase p. Draw a pedigree for a family where one parent and 2 of 3 children have a peaked hairline. Okay, so we have to have parents, dad and a mom, and they have 3 children. You can choose boys, girls, or a combination thereof. You just need 3 children. So I'm going to make a girl, a boy, and a boy. One parent and 2 of the children have a peaked hairline. So one parent, I'm just going to pick one of the parents, and 2 of the 3 children have a peaked hairline. Okay, and that's going to be colored in, and then the hollow will be the lowercase p. Okay. One of the children with a peaked hairline, so one of these 2, marries an individual with a smooth hairline. Okay, so marries somebody with smooth. Their children both have a peaked hairline. So they have 2 kids. Let's make it a girl and a boy. You can make whatever combination you want. And they both have a peaked hairline, so they're both colored in. Identify the genotypes and phenotypes of each individual. It's easiest to start with the recessive because that's all lowercase. Then go to the dominant, which has at least 1 capital letter. I'm exaggerating it because it's hard to tell with the letter P. Now, this family had 2 children with a capital P and 1 with all lowercase. So they got 1 lowercase from this parent. The other lowercase had to come from this parent. Then, if this parent gave a capital letter, this parent gave a lowercase letter. Okay, now let's keep going. They each inherited a capital P. The capital P had to come from this parent. Therefore, this parent had to pass on the lowercase p. So we've identified the genotypes, and the phenotype is colored in or not. So this is a smooth hairline and then and so this colored in is dominant, which is peaked. As a top research scientist, you and your colleagues have discovered a new sex-linked recessive condition. In the course of your research, you have come across a pedigree for a family in which the condition occurs. So this is a sex-linked condition. That means it's either on the X or the Y chromosome. It can't be the Y chromosome because here's a female who has the condition. So it must be on the X chromosome. Which individuals in the pedigree can you be certain are carriers of the allele? By the way, it's a recessive condition. Let's use a capital A and a lowercase a because it's easy to tell the difference between those letters. This is a female with 2 X chromosomes. And if she is showing this condition, she must have the recessive A on both of her X chromosomes. This is a male. He is XY. He has the recessive A on his X chromosome. All right, now if this female got 2 X's with an A, she got one of them from her dad and one of them from her mom. So we have a problem. They have incorrectly colored this. But I think that was on purpose, so you would have to figure out who's a carrier. This dad has to have the condition because there's no X to cancel out this X with the recessive condition. So he has this condition, whatever it is. The mom, she's female, she has 2 X's. She had the recessive A condition and she had a dominant X allele that was normal, which is why they couldn't tell that she had this condition. She is a carrier. So you fill this in halfway to show that she's carrying it, but she doesn't actually have it. She can pass it on to her kids. This is another daughter. She has 2 X alleles. This X from her father definitely has that recessive trait. She doesn't actually have the trait, so she must have received the normal X from her mother. So she has to be a carrier. You're probably noticing if the dad has this trait, the daughters are going to be the carriers. His sons won't have it and can't pass it on because they'll get the normal Y from him. Well, unless they get the abnormal X from the mom. So he's got another daughter. He had to pass on that recessive X. Mom either passed on the recessive or the normal. She must have passed on the normal because this girl does not have it, but she is a carrier. This guy definitely has an X and a Y, but what kind? Well, his son definitely got the Y from the dad. So that's what got passed on. The mom apparently passed on the lowercase a, the recessive X chromosome, and so that's what caused this guy to have this condition. Both of these are the letter X because they're, of course, both females. She got the normal X from the dad, because they couldn't get the Y because they're not guys. So the mom either passed on the recessive or the normal trait, and we don't know which one she passed on. So these may be carriers and may not. So now we have a female who does have the condition, married to a male who does not. So he has a normal X and Y. All right, let's see if you can figure out this last part. When this guy has a son, what does he have to pass on? When he has a daughter, what does he have to pass on? Then look at the mom. What does she have to pass on? And then who will have the trait, not have the trait, or be a carrier of the trait? Predict that as well. The carriers will be half colored in, and you've already explained why by showing everybody's genotype, so you don't really need to explain. If individual 3-3 has a son with a woman who is not a carrier of the allele, what is the probability that the son will have the condition? So individual 3-3, this person here, has a son with a woman who is not a carrier of the allele. So we will draw a Punnett square because that will explain. This man was XAY. The woman is not a carrier, so her genotype has to be XX. Now, do your cross. Well, it gets a little crazy here. First, they want to know if the son will have the condition. So if it makes a daughter, ignore it. So only look at the possibilities that make a male. Then, out of the chances that it could make a male, look at how many of those chances, what percent have the condition. So only look at the males, then figure out what percent have the condition. Number 5. In the pedigree below, different blood types are identified by the letters A, B, and O. All right, let's just do all the genotypes. It's easiest to do the recessive first. So what letters does type O have to have? O, double O. AB obviously has to have an A and a B. Then you've got to figure out the second letter for all the plain A's and the plain B's. Do they have a second A and a second B, or do they have an O? So with these parents, the dad could pass on an A or a B. The mom cannot. She has to pass on an O. So every one of these kids has an O as their second letter. Now for these two. These could be AA or AO, and this could be BB or BO. We don't know which one yet. If they have this kid with type A, the mom had to give the A. If this is the dad, and this kid is type A, the dad could not give a B. The dad would have to give the O. Dad has to be BO, not BB. Let's look at this kid. The B definitely came from the dad. The other letter came from the mom. What other letter does it have to be to let this be blood type B? Well, if she donated an A, this kid would be AB. She had to donate an O, and therefore her genotype is AO, not AA. Okay? Now, with these two, who did the B come from? Then what did the other parent pass on? Then finally, list all the possible blood types for the infant girls. So this is the dad, this is the mom. We need to do a Punnett square. The dad, B, O. The mom, A, O. So do your cross, figure out all the blood types, and then list your blood types here. Remember, there is no blood type BO or BB. It's type B. So make sure you list the blood type, not the genotype. Individuals 2-6 and 2-7 have a second child with blood type O. 2, 6, and 2, 7. So a second child, let's make it a girl this time, with blood type O. What does this tell you about 2-6's genotype? Well, we've already figured out the genotype from the parents, but that was a little challenging, so they're trying to help you out here. All right, if they got an O from this parent, they also got an O from this parent. I believe you can answer letter C on your own. You can either explain with a sentence or you can explain with a Punnett square.